Who is number 2?
Number 2.
Who is number 2?
I actually saw that. They're in
Yes. Okay. Everybody, shut your laptops. And again, you know the protocol. You don't open the laptops except for Piazza. So number 2, where did we end the class? The last class. Yeah. What was the last topic we did in the previous class? Pardon me? Oh, just trying to catch up, right? So what was the last topic in the previous class? Back propagation through time for bidirectional networks. So whoever has got this mumbling sound on Piazza, please on Zoom, please mute yourself. Please mute yourself, guys. Oh, all right. So today, here's the story so far. We saw that iterated structures are good for analyzing time series with short-term dependence on the past. So if I wanted to analyze time series in general, number 7, what was the problem with this model? Who's number 7? Yes.
We are not able to previous time points.
So this has very restricted history. It's a duration of history that it pays attention to that is very short. So who was number 21? How did we solve the problem? So we actually used recurrence, right? We wanted the state. We wanted some component of the model to pay attention to other units within the model itself. Now, we also saw a different kind of mechanism for trying to pay attention to past values. What was that? Number 45. Who's 45?
45 Zoom.
So who's 45 on Zoom? So there, what was the other mechanism we saw for using information from the past for making predictions? Still there?
Knox.
Yes. Okay. So what was the other
Knox.
mechanism that we used to
Knox,
refer to the past when you're making predictions?
Knox and ARX.
Knox, right? So the output itself, right? And we saw other kinds of mechanism ways. We also saw various memory neuron networks. Then I said, for example, that when we use Jordan networks, anything that Jordan networks is one of the examples that we used. We said it was not true recurrence. Can anybody tell me why I think it was not true recurrence? Yes. Wherever. So here is what we really need, right? There are two issues going on here. First is if you're referring to the output as opposed to an internal variable of the network, you have a problem. Which output are you referring to? Are you referring to the true output or the predicted output? Does the predicted output bear any relevance to the current output? It does not unless your prediction is perfect, right? If you're looking at the true output, is there any way of back propagating something from the true output back into the network? True output is just a number, right? It's just something else going into the system. So if you're trying to refer back to previous output values, there really isn't a true recurrence unless you're looking at predicted values, right? The moment you begin looking at predicted terms, then you're again referring to internal variables of the network. The other issues that we had was that when you actually have true recurrence, you might have something of this kind where maybe a small perturbation over here does not change the outputs here or here or here, but does end up cumulatively changing the output 5-time instance down. If that happens, then you need to be able to adjust your parameters to say that I need to make sure that my model captures this long dependence, right? And the other kinds of models that we saw, the Jordan networks and the Elman networks did not do that. So we saw the way we had to do it was to actually include proper recurrence of the kind that we saw in this model. Now, recurrent structures, we've explained recurrent structures as structures that are good for capturing time series and long-term dependence. But is that the only kind of problem where recurrence is useful? So let's look at a different problem. The problem of adding two binary numbers represented in bits as bit sequences. I want to create an MLP that can take in two bit sequences of length n and output the sum. How big is this model going to be? If I let you use only two hidden layers, for example, how big is this model going to be? Can anybody tell me? Yes. It's going to be exponentially sized if I have any finite depth, right? So this is not a very good model, right? Also, even if you manage to build, if I let you go deep, and if I let you build a finite sized model, which can add two n-bit numbers, can that same network be used to add two n+1 bit numbers, or will I have to construct a new model? I will have to construct a new model, right? On the other hand, if I do something with recurrence, it becomes much simpler. So here, for example, secondly, if I'm trying to train the model, if I'm constructing a network to learn the rules of addition, how much data will I require? If I'm summing two n-bit models, how much data will I require? I'm going to need every possible value before it learns the patterns, right? Learning is going to be an impossibly difficult task. Here's the recurrent version. The recurrent version is much simpler. Only rules it has to learn, something like this. If I'm adding A, B, and the carry. So this is bit 1, this is the bit 2, this is whatever carry might have come in from the previous value, and there are two outputs, right? The sum and the carry. So it's a very small 8 rows. How many training instances will I need to train this network? Just 8. And you can see what is happening. I'm adding it 1 bit at a time. And at each point, you're taking in the carry from the previous bit and the two current bits. And this will generalize. It can add numbers of any size. And it's going to give you an output. So you can see that this notion of recurrence can actually be carried to models and problems where you didn't think of recurrence as a natural component of the model. Here's another example, the parity problem, right? You know what the parity problem is. The output must be a 0 if there are an even number of ones, and a 1 if there's an odd number of ones. This is just the XOR, right? Now, what did we know about the XOR? If I limit the depth of the network, how large did the XOR circuit get? It was exponential, right? Now, suppose I just don't tell you that this is an XOR and expect you to learn the rules and correctly learn the rules of an XOR. And I'm looking at n-bit inputs. Then whose number? What is the largest one?
171.
Who's number 171? Yes. So if I wanted to train a network to learn this rule, how much data would I have to give it? Does anybody else want to tell me? I have to give it because there's no clear pattern over here, right? So you'd have to give it every possible combination of bits to learn the rule. You would need an exponential number of training instances. But suppose I wanted to do this with recurrence, Karen. How would I do this with recurrence? Pardon me? So I can't hear you. Can you? Maybe I can repeat what you're saying. So what was the state you said? So how can I do this model with this problem with network? So who is number 112? Who's 112?
Hello? Yeah. I'm
How would
Manuel.
you do this? How would you do this?
Sorry?
So I need to train a model. I need to build a model that can just compute the parity of an input sequence. I want to build a recurrent network for this. How would you do it? Does
I'm not
anybody else?
sure.
Yeah. So Philip,
You learn like an XOR for 2 bits and then you apply it.
this is it, right? You're going to look at it 1 bit at a time. That's it. And so for each bit, what is the rule you're going to learn? If the total number of bits so far is even, and the new bit is a 1, then the output must be a 0. If the total number of bits so far is ones is odd. I mean, if the total number of ones so far is even and the new bit is a 1, the output is a 1, right? Because now I now have an odd number of ones, and vice versa. So basically, the actual this recurrent model is simply going to learn. This is my carry. This is my input. This is my output. 0, 1 is 1, 1, 0 is 1, 1, 1 is 0, 0, 0 is 0, right? I just need to learn this very simple thing. So after every bit, I'm going to generate an output. That output goes back into the network. The simple parity circuit, which we made such a big to-do about in the second class, is a very trivial recurrent circuit. Is this making sense to everybody? So can somebody explain what is going on over here? Who's brave? Tomas? What am I saying over here? What is the model here? Okay, so if I wanted to if I wanted to compute the parity of a 4-bit sequence, how would this do it? Bit by bit, right? So I'm going to just have, initially I'm going to give this a 0. This is my B0. There's an output that goes in here. This is B1. There's an output that goes in here. This is B2. There's an output. I'm going to go in bit by bit, and it will always give me the correct answer. And to train the model itself, I only need 4 training instances, right? So you can see, because there are only 4 rules to learn. So you can see how something that's a really complicated problem using MLPs suddenly becomes trivially simple just by using natural recurrence in the problem. So it's not just time series that recurrent models are useful for. Anywhere you have natural recurrence in the problem, these things apply. Everyone with me? Right? Okay. If you aren't, the poll will let you. How many so far?
48. Oh, number of people. 186. 185. Shall I close the form?
Close. Okay, 10 seconds, guys. That 48 isn't showing? Okay, that's all right. So then you don't need time. Here it is. Some prediction and classification problems that require very large MLPs and large amounts of training data can be solved using small recurrent networks which need tiny amounts of training data to learn, right? We just saw this. And something that requires very large, complicated convolutional neural networks can also be done very simply using recurrent neural networks. We saw this in the last class. So here's our story so far. Recurrent networks are good at analyzing series problems or problems that can be cast as series problems. And to train them, they can be trained by minimizing the divergence between the sequence of outputs that you get and the target sequence of outputs. This too we saw in the last class. Now, let's go right back over here. This is the old problem, old network. Who's number 61? Who's 61?
Yeah, right here.
Yeah. So what was this? What was this model called?
The one on the screen, TDNN.
It was a TDNN, right? And will the output of this model, if I use say ReLU or your standard activation functions, if I guarantee that all the input values are bounded, will the output ever blow up?
No.
Why not?
I mean, I guess it just if the input is bounded, I guess I don't see where would it blow up in
Absolutely,
that.
right? This is what is called bounded input, bounded output, stable, meaning if the function has bounded output for bounded input, which is true of every activation function, then if the inputs are bounded, the output is also going to be bounded. This is what is called bibostable, and this is a highly desirable characteristic. You don't want your network to suddenly blow up and have increasingly large values or get saturated when your inputs are perfectly reasonable, right? So this is a requirement. Now a network of this kind, who is number 91?
That's me.
Okay, would this be Bibo?
I don't think so, because if the input is constant, the output will be growing unboundedly without bound.
Yeah. So if you could potentially have outputs that keep growing continuously.
Yeah.
So thank you. So this is guaranteed to not blow up if the activation saturate, but saturation in some senses is loss of information too. So blowing up is not what we should be looking at. Does it lose information about the input? Very definitely can happen, right? So this is, so let's try to see when this thing can blow up, right? Because this is for this kind of model to be useful, you want to have some assurance that the output is not simply going to go into the sky, even as you're giving it reasonable inputs. So we will analyze it, but then which portion of the model do we actually have to analyze? Number 45. Who's 45?
45 is actually done.
Okay, doesn't matter. 45. So 45 is missing. All right.
Sorry, come again?
So which portion of this network would you actually have to analyze to figure out if it's stable or not?
The orange portion.
The recurrence, the green portion, that's where you're feeding back on the previous output, right? The previous values. To find out if the network is stable or not, you need to look at the recurrent portion. Now, the problem is that these networks can get very complicated depending on the activation function. So we're going to use the streetlight effect. We are going to analyze what we know how to analyze. We're going to figure out when those things behave properly or misbehave. And based on that, we're going to build our hypotheses. Okay, we've done this before. So I'm going to analyze linear systems where all the activations in the recurrent layer, we're not looking at the output layer, it's the recurrent layer, where I'm going to analyze a linear system where the activation function of the recurrent layer is linear, which means that the output of each unit is simply an affine function of the inputs, which is these guys, right? So at any time, the hidden value is simply the affine value itself. And the affine value at any time is simply an affine function of h of t minus 1 and the current entity. Okay? So for this to be stable, here is the requirement I will have. If I give it an input at an initial time, this is a linear system, right? If I give it an input at time 0, then the output should not blow up no matter how far down I go. If I can guarantee that, then the system is going to be bounded input, bounded output stable. And so we will see how or under what conditions this holds, right? So here is how the system behaves. So in general, we have said hk is wh times hk minus 1 plus wx xk, which is to say it's an affine function. I'm ignoring the bias over here. I can always think of the bias as an extra term as we saw in our input, remember? So I'm going to say that the hidden value at any time, k, is a linear function of the hidden value at k minus 1 and the current input. But then hk minus 1 is in turn simply a function of hk minus 2, right? And so now I can plug in the second equation and the first equation easily. And if I plug it in, what is the relationship going to end up looking at like? Can someone tell me? I want to write hk in terms of hk minus 2. So who is number 33? How would I write it? So just tell me the equation. So it's WH squared times HK minus 2 plus WH times WX. Wait, WH times what? XK minus 1, right? Plus WX XK, right? So now can somebody who is number 150? Who's 150 on Zoom?
Can you hear me?
Yeah, so can you tell me how I can write HK in terms of HK minus 3? So I've just written this down here. How can I write it in terms of HK minus 3? Because HK minus 2 is a function of HK minus 3. So how am I going to write it? 150.
So you just plug in hk minus 2 as a function of hk minus 3.
So can you give me the equation?
Sure, it would be WH squared
Times WHXK minus HK minus 3, right?
right?
Plus WX XK minus 2, is it right? And plus the remaining, if I actually expand it out, that's going to end up being WH cubed HK minus 3 plus WH squared WX XK minus 2 plus WH WX XK minus 1 plus WX XK. So does anybody see a pattern over here? In the end, can I write my WH entirely in terms of X, WH, in terms of the X? Because I can write HK minus 3 in terms of HK minus 4. I can write HK minus 4 in terms of HK minus 5, right? I can keep going backwards. Yes. Pardon me? Because this WX being, you think of WX times X as a comp. Oh. Is there any additional use of WX coming in at any point? It's not, right? Just work out, look at the arithmetic. It's fairly straightforward. I'm not actually adding anything, right? So can somebody tell me the generic formula for this? I'm not going to, yes. It's going to. Yes. So I don't want to have the H at all. So what would it be? Eventually, I can write this. I can write this all the way back to HK minus 1, right?
You have plus summation from I equals 0 to H or I.
Okay, but he's got the equation right? But I have it on the slides. Yeah. So eventually I can unravel it all the way back to the initial value of H, and then look at what happens. It's just WH times raised to K plus 1 times the input, right? At time 0 plus WH raised to K times the, it's WH raised to K times X0 plus WH raised to K minus 1 times X1 and so on. So it's generally going to look like something plus summation K WH, N K minus N Xn, right? That's the form it looks like. Now, let's look at this. That first term is the input response to an input at X0 at time 0. So if all I had was X0 and no further inputs, the subsequent terms are going to be 0, right? And so if I write that first term as the response of the system to an input at time 0, then the second term is the response of the system to an input at time 1, right? The third term is the response to the system at of the system to an input at just time 2, and so on. So I can write the whole thing in terms of the response to the initial value plus the response to the input at time 0 plus the response to the input at time 1 plus the response to the input at time 2, and so on, right? If the system is stable, will any of these things blow up? Right? None of these should blow up, right? Now tell me this, which of these terms, if I have to pick just one term to focus on, which one would I focus on? Pardon me? WH, the very first value, right? I just need to look at this guy. If you look at this, each one, if I think of the response, firstly, it's a linear system. So if I think of the system as, if the input being 1 at any point, scaled by whatever x value, I've just sort of fully rewritten it in terms of a response to a unit input at every time, okay? I only need to be focusing at the input to the response at time 0. Because if a response to a single input at time 0 blows up, the system is going to blow up, right? And if the response to the input at any further time blows up, then clearly, right, it should have also blown up to an input at time 0. Because all of them, if you look at all of those guys, there's some fixed values, fixed scaling or some bounded scaling times the response to a unit input at different times. So I don't know if you can see this. This guy says it's x0 times the response to a unit input at time 0 plus x1 times the response to a unit input at time 1, and so on, right? So if the response to the unit input at any time blows up, it's going to blow up, right? And because you're looking at the response to a unit input, so I don't know if I'm getting the point across, but if this is my time, then I can have unit inputs at any given time, right? And if the response to this guy blows up, then clearly the response to this guy must also blow up. Because they're all these delayed versions of the same thing, right? So all I need to do is to say, check if the response to the first time, to a unit input at time 0, if that blows up, it means the system is unstable. If that doesn't blow up, it means nothing blew up, right? So let's just focus on the first guy. What is the first guy a function of? That very first term, right? This is just the principle of superposition in linear systems. So all I need to do is to worry about what happens to the response in response to a unit input at time 0. And let's take a look at that. I'm going to write this. I'm going to try a very simple system. I'm going to say that ht is w times ht minus 1 plus txt. And I'm going to assume that there's a single input at time 0 and no further times. Because what we've established is that if we can show that the system is stable when I have a single input at time 0 and no further inputs, then it's always going to be stable, right? Because it's a sum of a bunch of bounded outputs. And so let's look at what happens if all I have is a single input at time 0, right? If I have a single input at time 0, here's what I get. At time 0, assuming that the initial value is 0, then I'm going to say h1 equals W times is going to be Cx0, right? H2 equals W times Cx0. H3 equals W squared times Cx0. H4 W cubed times Cx0. As you can see, what is happening is that because I only have an initial value x, a non-zero value for x at time 0 and all subsequent x's are 0, the output at any time is simply going to be at time t simply going to be w raised to t times Cx0, right? I'm off by 1. So this, when will this blow up? Yeah. If w is greater than 1, this is going to blow up, right? And what will happen if w is less than 1, number 99? Who's 99?
No, there's no.
There is no, you guys have been skipping numbers. Very clever, right? Who's 98?
Hi, Professor. I'm 98.
So what would happen if w were less than 1?
It will go. It will be less and less.
It would keep going down and eventually
Yeah.
the output is going to vanish, correct? So
Yeah.
here are the behaviors for different values of w at the plot below. And what we see is that when w is less than 1, the value that you give at time 1 goes to 0. Is if w is greater than 1, the value just blows up to infinity, right? So this is for scalar functions where w is a simple scalar. I can do the same thing for vectors. If my x and h are vectors, the behavior is much the same. I'm going to have, if x0 is a vector, h0, right? H1 is going to be w times x0, h2 is w squared times x0, ht is going to be w raised to t times x0, where w is the weights matrix, the recurrent weights matrix. And moreover, I can write w. Remember, the recurrent matrices are always square because the input and output are the same size, right? So you can, using eigen decomposition, I can always write this as u lambda u inverse, where u represents the matrix of eigenvectors, and lambda is a diagonal matrix of eigenvalues. And so writing the same thing in this manner, ht is going to be u times lambda raised to t times u inverse times Cx0. Does everybody see this over here? I've just used simple eigen decomposition, right? What is the condition? So over here, what will happen? If any of the eigenvalues is greater than 1, what is going to happen? So let's say lambda, this is simply going to be lambda 1 raised to t, the rest are 0. This is lambda 2 raised to t. Each of the lambdas are going to be raised to t, correct? So if any of the eigenvalues is greater than 0, greater than 1, what will happen? That thing is going to blow up, right? And moreover, if you look at specifically, if you look at what happens, I can write any vector as a weighted, as a linear combination of all of the eigenvectors, right? So I can write any vector u. What this here is, did I just drop my chalk? Where's my? Okay. So this may end up, this may look a bit complicated, but just bear with me. There's a point to all of this. And so that's this, that if in general, all of the eigenvectors span the space, right? So I can write any vector x as some a0 times eigenvector 0 plus a1 times eigenvector 1, etc. Any vector x can be written in terms of as a linear combination of the eigenvectors. So wx is going to be a0 times wu0 plus a1 times wu1 and so on. And what is this thing over here? These are eigenvectors, correct? So what is w times an eigenvector? It's just the corresponding eigenvalue times the eigenvector itself, right? So I can write this as lambda 0 times u0 lambda 1 times u1 and so on. Correct? Everybody with me? Right?
Sorry,
In general,
Professor.
if I have the w raised to t times x, what will this become? It's just going to become lambda raised to t, right? Because each time I'm multiplying the u's, the w's, right? Take a look at what happens. I have wx. So w squared x is going to be a0 times lambda 0 times wx0 plus a1 times lambda 1 times wu0, right? u1 and so on. And again, using the same rule, wu0 simply lambda 0, so this is simply lambda squared, lambda 1 squared. So what happens is that as you keep multiplying the thing by w, one of these w raised to t times the vector x simply becomes whatever factor a times the corresponding eigenvalue raised to t times the corresponding eigenvector, right? For each of these. Now, over here, this is an exponentiation with time, right? If I have two eigenvalues which are just slightly apart, what will happen to the gap between them as t increases? It's going to keep increasing, right? In the end, eventually, what will remain? Somebody answered. What is that? The only term that will remain is going to be the eigenvector corresponding to the largest eigenvalue. The rest of them are going to be minuscule in comparison and will eventually vanish, right? So in order to analyze the behavior of this recurrence, I only need to look at the eigenvalues of the system. And if the largest eigenvalue of the system is, basically I have to look at the largest eigenvalue of the system. If the largest eigenvalue of the system is greater than 1, what will happen to the response of the system? If it's less than 1, it's going to disappear, right? So for any input, the length of the hidden vector will expand or contract according to the kth power of the largest eigenvalue of the recurrent weight matrix. And moreover, if this largest eigenvalue is greater than 1, it's going to blow up. Otherwise, it's going to contract and shrink to 0 very rapidly. And so here are some examples. Here, these are vector recursions. We have a single input, which is just a vector of 1s at time 0. And you can see that in the left-hand side, the largest eigenvalue is 0.9. And you can see the response is the length of the hidden response just goes to 0 very quickly. In the one in the middle, I have one. In one case, the largest eigenvalue is 1. In the other case, it's greater than 1. You can see when it's greater than 1, it just blows up. When it's 1, it sort of oscillates. Why is it oscillating? Can anybody tell me? Pardon me? Complex eigenvalues will just cause an oscillation around the central point, right? And if they're completely real, you're going to have behavior like the thing to the right. So you can see that in order to analyze the response of this network, of this model, if the hidden activations are linear, the long-term behavior depends entirely on the eigenvalues of the recurrent weight matrix. If the largest eigenvalue is greater than 1, the system is going to blow up. If it's less than 1, the response will vanish very quickly. Complex eigenvalues can cause oscillatory response, but with the same overall trends. Magnitudes greater than 1 will cause the system to blow up, right? So the rate of blow up or vanishing depends only on the eigenvalues of the hidden of the matrix. It does not depend on the input itself, right? It all depends on lambda raised to t. So how long will the system remember an input? Eventually, what is it going to remember? Either what it remembers is going to blow up or it's going to go to 0, right? If you wait long enough, the system has no recollection at all of what the input was because the thing has either died or blown up to infinity, right? So we have a problem. But then we don't have linear activations, right? We actually have non-linear activations. So what happens if I introduce a non-linear activation? What happens if I introduce a sigmoid and I say that at each point, the actual system is, ht is sigmoid of wht minus 1 plus cxt plus b, right? Now I've also explicitly introduced the bias just to make things clear. When will the system respond? What happens to the system? So here's what will happen. Suppose I just give it a single input at time 0 and I have no further inputs. Then the hidden activation is going to be something of this kind. You're going to say HT is sigma of whatever W times HT minus 1 plus B, right? When will this be stable? Will it ever become stable? It will, right? It's going to be H, I can say H equals sigma of WH plus B. I can write out the equation. There is a value H where this equation will be perfectly satisfied, which means that at that point, further steps through time are not going to change H, right? What is the value H at which this happens? Does that depend on X0? Does X0 occur in this equation? No. So what is the value of H where it stabilizes? It's a function of W and B, correct? So I can actually write this out. This is some kind of an equation where I'm solving for H, and the terms that affect the solution are W and B, right? So what happens is that the final value that happens, that you get, depends only on B and W, but not on X, right? So I have this table of plots for different values of W, different values of sigma. And what may not be apparent is that in every case, as you go through time, the system basically saturates and keeps repeating the same value after a while. And the specific value that it repeats has nothing to do with the initial X that you give it. It only depends on W and B, right? This is when I'm using a sigmoid activation. And observe how quickly it forgets the input. In literally about 3 or 4 time steps, there is no information left about X at all in the hidden value. The only information left in the hidden value is something to do with W and B, right? Similarly, if I use a tan H activation, I get the same behavior, because all that happened is that I'm going to get H equals tan H of WH plus B, right? This is an equation which has a stable point. The stable point H at which this stabilizes depends only again on W and B, right? So what it eventually keeps track of has nothing to do with the input that was given, right? The one thing about tan H is that if you compare tan H to sigmoids, the amount of time it takes before it saturates is slightly longer, right? So yes. Take a look, right? This is literally the equation I've given you. So this is the recurrence. This is the recurrence, right? Sigma maybe whatever activation. When it stabilizes, you're going to get this behavior, correct? Is the solution to this dependent on X? Right. It's only in? But how long does it take to get stable? 3 steps, right over here. Tan H takes a few more steps. And so very quickly the input is forgotten. Correct? What is the question? So I had just one input at time 0, and thereafter it was always 0, right? So I'm trying to see how long it keeps track of an input at time 0 with no further inputs. Right? Yeah. No, W is the recurrent weight, B is the bias. But the point is, it's a statistical aggregate. It doesn't depend on any specific input. Right? Yeah.
You have the same question. So like no matter what we put in with this model, after a certain number of iterations, it's always going to be the same value.
Absolutely, which depends only on B and W, right? And so if I use a ReLU, a couple of things happen. If the input is positive, it's going to blow up because ReLU is simply WX, right? If the input is positive and W is greater than 1, it's going to blow up. If W is less than 1, it's going to die to 0. If the input is negative, the output is always 0. The point is there's nothing about the output that carries information about the input after a couple of steps, right? So these are scalar. I can do the same thing where W and C and D are vectors, and I can run through the entire simulation. I have a whole bunch of pictures over here. The story remains the same. The story is that in every case, after a few steps, if you're using either a sigmoid or a ReLU activation, the hidden value saturates to some value, which only depends on W and B and not on H, because regardless of whether you're looking at a scalar function or a vector function, the stable point of this equation depends only on W and B, doesn't depend on X. Right? Everybody with me? It has a unique stable point, and that stable point is only on W and B. Right? Yeah. Look at the picture to the left. For each of those 4 or 5 plots are for some value W. I forget what the value W is. There are 5 different B's, right? I gave it an input at time 0, and then just kept recursively computing the H. So and that's showing the length of H. What's happening over there? It's saturated, right? Yeah. So what is the lesson that we got out of this? Can anybody tell me? That's a good lesson, but pardon me? Stable, they're all going to saturate, some, right? Eventually, right? The actual lesson that you learned is that these things don't really remember your input, right? What they remember has nothing to do with what you feed it. What they remember has to do with the parameters of the network, right? Statistically learned parameters of the network. Yes, Philip?
Yeah.
Yeah. So, and these are for different kinds of, in every case, I've shown the plots for different values of the eigenvalues of the recurrent activation, recurrent weight matrix. It doesn't matter what you give it. Yes. After a few steps, what it retains in memory, which is the recurrent state, is more a function of the network parameters and basically not even a function of the input. Yeah,
We learned this the way we back to the function.
but then it's also about an entire training set. If you're trying to perform inference on a single instance,
Okay.
right? When you're performing inference, it's about a single instance.
Okay.
At every point, all it's going to give you is the statistical aggregate of your entire training set. Is that really what you want? No, right? You want point by point inference, right? You can't get, yes.
Saying that the memory lies in the parameters, isn't it the definition of the regular connection?
It's not in Boltzmann, right? But the point is, the whole point is that there is no dependence on what is remembered on what you're trying to remember. And this is a definite problem, right? Now, so if you want to do it, if you want to do it formally, you have to look at Routh's criterion, pole zero analysis, etc. What we find is that the bipolar activations like TAN-H retain information for the longest period of time, which is why we usually use TAN-H activations in recurrent networks. But even TAN-H is basically saturate and give you something useless after a few times, a slightly longer time. So here's a problem.
Hello, Prof.
Yeah.
Can I ask why are we assuming that W is diagonalizable?
Pardon me? Why
are we assuming that W is diagonalizable?
We're just saying that W is a square matrix. And if W is a square matrix, you can always perform eigen decomposition. That's it, right?
Is that true?
Yeah. You may not have unique eigenvectors, but you can always write it as U inverse. Yeah.
That the eigenvalues are all like 1 or that.
If the eigenvalues, that's a very, very sensitive stable point, is it not? And, yeah, and so what there is, we're not looking at degenerate matrices at this point, right? there are situations where things degeneracy can happen. I can always do a singular value decomposition, and I can explain things in terms of singular values. You end up with the same kind of behavior. So anyway, so what we found is that an RNN can retain some memory of an input pattern, but how long it retains depends on the weights of the recurrent layers. It depends on the eigenvalues of the recurrent layers, and it depends also on the bias of the recurrent layers, as we saw it. But beyond a point, and it depends on the activation function, but what it eventually remembers after a few steps is not a function of the input. It depends on the weights, it depends on the bias and the activation function. What is missing from the second answers to the second question is the input itself. What the hidden layer remembers after a certain amount of time depends on everything except what you're trying to remember. Right? So that's not a good state of affairs. Yeah.
So the weights and the biases don't affect what it remembers, but how long it remembers?
Yeah, in the sense that if you look at these guys over here, if you look at these plots, you can see that the time taken to hit saturation is a function of the weights and biases. I mean, you saw that if the eigenvalues are very close to 1, it's going to remember things for a slightly longer time. If it's 0.99, it's going to remember things longer than if the eigenvalue is 0.5, right? But eventually it's going to forget. So it depends on the duration, depends on the eigenvalues. And as Alex pointed out, if I had some constraint which said all eigenvalues are 1, maybe you get something useful, right? So then you can also have other kinds of instability. Now, here's another problem. So here's the story so far. Recurrent networks retain information from the infinite past in principle. That's the hypothesis we began this whole story on, right? But in practice, they tend to either blow up or forget. If the largest eigenvalue of the recurrent weight matrix is greater than 1, the network response can blow up. If it's less than 1, the response dies down very quickly, right? The memory of the network also depends on the parameters and the activation of the hidden units. Sigmoid activations saturate very quickly. ReLU tends to blow up or vanish rapidly. TANH is slightly more effective at storing memory, but in all cases, if the output is not blowing up or dying, then the value at which it saturates depends only on the parameters of the network. The stable value doesn't depend on the input that you're trying to remember, right? So that's a problem. So what we've seen is that RNNs are hypothetically excellent models for time series, prediction, classification, sequence generation. They can even simplify problems that are difficult for MLPs, but the memory is not all that great. But then here's another problem that happens, right? A particular problem with training deep networks, any deep network, not just recurrent networks, is that the gradient of the error, the loss, with respect to weights is unstable. Why is that? So here's how this equation on the slide may not be very clear, but then here's how I can write it, right? Suppose I have an input X, and then you have the first layer activation weights, then I have the function F, I have the second layer activation, then I have another function F2. So this is your standard network, correct? So what is the output? I have X, W1X, F1 of W1X, W2 of F1 of W of X, F2 of, so W3, F3. This is the actual computation in the network, correct? So this is the first the weight matrix. This is the output after the first layer activation. These are the weights applied to the output of the first layer activation. This is the second layer activation. These are the weights for the third layer. This is the output of the third layer. The network is actually a very deep nested function, right? And so that's going to be the nature of the network. Y equals Fn of Wn times Fn minus 1 and so on. Just writing the network as a nested function. The divergence is an output of the network, function of the output of the network. The divergence too is a nested function. And now, here is a standard rule, right? Vector, I have the derivative chain rule for vectors. If I have some f of w of g of x, we're speaking of nested functions, right? That's so f of w of g of x has the form that we have over here. So then the derivative of f with respect to x is going to be the derivative of f with respect to wg times the derivative of wg with respect to g times the derivative of g with respect to x. That's the standard chain rule, correct? Which is going to be, if I write wg as z, then it's going to be f, the derivative of f with respect to z, the first derivative term. Then the derivative of wg with respect to g is just w, right? So the second term is w. And then the third time is the derivative of g with respect to x. This chain rule has got to be very familiar to all of you, right? Nothing particularly complicated. So if my function, outermost function f is my divergence, then this is going to give me the derivative of the divergence with respect to the various terms in the network. And at any point, this derivative of f with respect to z is going to be the Jacobian of f, right? The derivative of g with respect to x is going to be the Jacobian of g. Those are all the Jacobians. So now, if I actually write out the derivative of the divergence of x with respect to x, that's going to be the derivative of the divergence with respect to the output of the network times the Jacobian of the output activation function of the network times the weight matrix for the output layer times the Jacobian for the penultimate layer times the weight matrix for the penultimate layer times the Jacobian for the previous layer times the weight matrix for the previous layer. That's how I can write the whole thing out. So everybody see where this is coming from, right? Is this equation clear to everyone, right? Very straightforward, right? So here is what I can. Now let's consider these Jacobians. These are the Jacobians of your activation functions. Now, what is the Jacobian? What is your typical activation function? It's either a sigmoid or a tanh or a ReLU or one of those, right? So if I have a Jacobian of a scalar activation function, which means that every value's output is computed only from the locally from the input, then what is the shape of this Jacobian matrix? Is it a full matrix or is it a diagonal? It's diagonal, right? What is the largest value of the diagonal elements? It's going to depend on the activation function, but yes, typically your Jacobian is going to be a diagonal matrix for these hidden layers, right? Furthermore, the diagonal entries are going to be the derivatives of the individual activation functions, right? And those guys, in turn, what do they look like? If I've got, for example, a sigmoid activation, then the derivative of the sigmoid goes from 0 to 0.25 and back to 0. If I have an tanh activation, the derivative goes from 0 to 1 back to 0. If I have a ReLU activation, the derivative is either 0 or 1, right? So given this, suppose I have some vector, and now let's go back and look at this guy, right? Look at the derivatives. So when I'm starting to compute my derivatives, I have my initial derivative of the divergence with respect to the output of the network, right? The next thing that happens is I multiply by a weights matrix. So I get some vector over here. Now I multiply this by a Jacobian, and this Jacobian is a matrix, diagonal matrix, whose diagonal entries are either 1 or lesser than 1, right? What can you tell me about the length of this vector versus the length of this vector? What's going to happen? It's always going to shrink because I'm multiplying the vector by a diagonal matrix whose diagonal entries are less than 1. They're going to be scaling down individual components of the vector, correct? And so what will happen here is that multiplying by the Jacobian is always a shrinking operation. Every time you multiply this derivative vector, every time the derivative goes past the Jacobian, it's going to shrink in length, right? Now, same thing. So as we go back in the layers, the Jacobians of the activations constantly shrink the derivative. After a few layers, derivative at the output basically becomes 0 by the time you get back to the input, right? The only thing that can save you, what can save you here from making things 0? The weights matrix. You still have the weights matrix, right? But then what do we know about the weights matrix? This is a recurrent weight matrix, right? You've got to focus on the weight matrix. Going forward, what kind of behavior did we want from the weight matrix? If the eigenvalues were greater than 1, what happened? The network output saturated. If the eigenvalues are less than 1, it vanished. Which of these two behaviors would you prefer? You would rather have it vanish a little bit. You want it to be just slightly less than 1, right? So what's happening going backwards over here? Every time you multiply the derivative by the weight matrix, what happens to the length of the vector? It still shrinks, right? You may have some eigenvalues which are greater than 1. For those components, the derivative is going to become larger along those directions, along the eigenvectors along the directions of the eigenvectors corresponding to eigenvalues greater than 1. The derivative is going to get slightly longer. In every other direction, the W matrix is going to make it smaller. The Jacobian is always going to make the derivative smaller, right? And so what will happen is that if you look at each term which represents one layer, the chain product will expand the derivative at the output in directions where each stage has singular values greater than 1. It's going to shrink it in each stage where it has in each direction where the singular values are lesser than 1. And in the majority, if not all of the directions, the singular values are going to be less than 1, right? And so as a result, the gradients of the lower layers show strange behavior. Along most directions, the gradient is going to shrink to nothing. And then there are some directions which correspond to directions with singular values greater than 1, the gradient is going to blow up. And so the entire thing is going to get insignificant derivatives go up at the beginning, or you're going to have unstable and very large derivatives. You don't have anything in between. And this problem gets worse as the network depth increases. So if you don't believe me, here are some examples. This is a 19-layer MNIST model. The output layer is at the bottom, the input is at the top. And this is at the very initial iteration, when you expect all derivatives to be the largest because you actually haven't performed gradient descent and gone to a value, right? And so the shade shows you the value of the derivatives for the sigmoid activations, for ELU activations. And you can see what happens across the batch. You see at the very output layer, you have reasonable derivatives. As you go back through the layers, by the 5th layer, all the derivatives are basically gone, right? So, or this one is with ReLU activations, same thing, everything disappears, right? And this was sigmoids. As you go through the layers, again, the derivatives after just about 5 layers, the derivatives disappear. Now that was TAN-H, same thing. It doesn't matter what the activation is. What you find specifically is that if you look at the patterns at the bottom, they persist for the longest time when you use ELU activations. For the other activations, they disappear after just 2 or 3 layers, right? Now this is for a batch. If I look at individual instances, you get the same kind of patterns. What you find is that as you go back through the network, after a few layers, the derivatives have disappeared and gone to 0, right? So you have this issue that in very deep networks, if you're trying to train the network going backwards, the derivatives simply disappear. And what is this? They don't all disappear. Something strange happens. Most of the derivatives will disappear. What you're not seeing over here is that you have 1 or 2 very bright spots. And those are the directions where the derivative is just basically blown up to infinity. So you have a very small number of exploding derivatives, and the rest of the derivatives basically disappear, which really means that you end up figuring out that there are just 2 or 3 terms in the input which are going to change the output. The rest of them don't even matter. Now, this is not very conducive to learning networks, right? This is not the kind of behavior you want. You want something more stable. And don't forget that, so in all cases, the gradients effectively vanish after about 10 layers. The results may vary. And both batch gradients and gradients for individual instances disappear. In reality, a tiny number just blow up, right? And So what we find is that recurrent networks are poor at memorization. The hidden outputs can blow up or shrink to zero depending on the eigenvalues of the recurrent weight matrix. This is when going forward. Also, going backwards, deep networks suffer from vanishing or exploding gradient problem. The gradient of the error at the output gets concentrated into a small number of parameters at the input. Now, what kind of a network is a recurrent network? It's a very deep network, right? Which means that some error that occurs out there is going to have absolutely no effect at all on the derivatives up at the input to the network. So this problem of vanishing and exploding gradients is particularly dramatic for recurrent networks. So recurrent networks being very deep networks, the relationship between x0 and yt is one of a very deep network. The gradients are going to vanish or explode by the time you get all the way back there, right? And don't forget what was going on when we went forward. When we went forward to the thing, like to forget everything and end up at a value which didn't really carry any information about what it is you were trying to remember, right? So after having spent the better part of 90 minutes in the last class and the first half of this class telling you recurrent networks are great things, I'll just spend the rest of my time telling you they're horrible things, right? They don't do what you want them to do, and they can't be taught to do what you want them to do. So when you get something of this kind, what do you do? Yes.
Sure, I can get connection to like something like ResNet.
Yeah, but you still have the business of things being forgotten, right? So the point is this: what is the cause of all of this grief? It's the cause of all of this grief is that it has parameters, right? Now, so let's solve this problem. Let's get rid of the parameters. The issue was that what the network, you want to have this network which learns to remember things, right? But the problem is, okay, first you have a poll, that's a problem.
Oh, may I ask that does batch norm solves the problem?
Batch norm solves the problem in part for very deep networks. But then it causes exploding gradients. Batch norm actually exacerbates the problem of exploding gradients. It eliminates the problem of vanishing gradients and replaces it with a different problem. Actually, yeah, I mean, it's a little more complex than that. Let's take that offline. 5 seconds, guys. I'm running out of time. I have only 13 minutes left in class. Okay, I know, right? So this was an evil problem, but here's the point. The derivatives for most parameters become vanishingly small as we backpropagate loss gradients through deep networks. The derivatives for a small number of parameters will blow up. The derivatives of them would be more stable if the recurrent weight matrix had singular values 1, which is basically what Alex was saying, right? What is the best recurrent weight matrix we can have? An identity matrix. It doesn't do anything. It's very stable, right? It's very stable. And so that's what we say. That's what the fourth statement says. What about the Jacobians? Do we like the Jacobians? So what do you want the Jacobians to be? Also identity matrices, right? So the memory is limited because the recurrent weight matrices are not unitary with eigenvalues equal to 1. It's limited by nonlinear activation functions. It would be more stable if the recurrent weight matrix was identity. It would be more stable if the Jacobian was also identity. Let's build a network with that. Okay? Everybody with me, right? Okay. We are fixing problems by eliminating the network. So what kind of network would have this behavior? I'm going to have a network which takes an input maybe, right? And then I get some memory at some time. But then this is time. What do I want this weight matrix to be? 0, identity, right? Meaning there is no weight. Yeah? And so my network is going to be something of this kind. There are no weights, there are no activations in what I'm trying to remember. But then what is this? What is it doing? It's not really doing anything useful, right? So let's fix that as well. Remember, so the example I'd like to take over here is that when you build a network, you like it to remember things, but it has a very specific behavior you want. Imagine I'm writing a recurrent network to parse C code. Then if it has detected an open brace, it has to remember that a brace has been opened. But how long does it have to remember that? Until the brace is closed, you have no idea when the brace will be closed, right? You can't just let it forget. That's a useless network, right? At the same time, if I get more braces in between, what must it do? It must increment the number of braces that it has remembered, right? So now you want the memory behavior to not be dependent on the parameters of the network. You want the memory net behavior to be dependent on the inputs, the patterns it finds in the inputs, and when is a closed brace relevant? If there's already a brace at the input, right? So here is what we're going to do. We're going to have Tales of Mystery and Magic. We just solve all our problems like so. The memory retention depends on these nasty terms. We're going to get rid of them. So skip this. Here's our picture, right? Our network is just going to be a pass-through network. Our memory CT is going to just go through unmodified by weights, unmodified by activations, just plain. But then it's going to be modified by something else. It's going to be modified by external signals, which will say, I've detected a closed brace, decrement the number of braces. I've detected an open brace, increment the count of braces. That makes sense, right? And this is the kind of memory behavior that you really want, right? So here is the entire network. This is going to be our constant error carousel. That's the name it's given. I don't know where it comes from, so we'll live with it. It's basically a network which has the memory is carried through uncompressed, no weights, no nonlinearities. You have scaling through these gating terms, which modify what's in the memory based on what has been discovered in the input, right? And so you have the actual nonlinear work. Now, it's not enough to have this. You need to be performing nonlinear tasks. So this memory is going to be acted upon. The memory is a separate structure that carries information about the past, and then additional nonlinear operations on what is in memory is going to be performed by other components of the network, right? And what is, neurons that compute some workable state from the memory? What is the network itself going to be triggered by? That gate which decides, modifies the content of the memory. That's going to depend on the current input, but also what is already in memory. Do I already have a brace? Because if I don't have a brace, there's no point in responding to closed braces, right? Then maybe other stuff, anything else that determines the context, right? And so this whole circuit, and including, of course, what might be in raw memory, right? So there are all of these different triggers. What do I currently hold in memory? What is the other processing the network has done? What is the current input? What other context do I have? All of these are going to determine whether I find patterns which modify what's in memory. Make sense? Right? So this gives us our long short-term memory network. If you ever wondered what the rationale behind an LSTM was, this is really what the rationale behind it. You don't want the memory to be affected by the parameters of the network. You want no parameters over there. You want the memory behavior to be dependent only on the inputs, right? So I'm going to go a few minutes over, guys, but then spring break. So, here's how we typically. I'm going to use this illustration from this web page over here, Colab Bio. So that's your standard recurrent network that we've seen so far. That the current hidden state and the input are going into the activation function, where you typically use a tan H because tan H is you retain memory the most. And that output is going to your output layer, but it's also going to be passed on forward to the next time instant. That little green box is what we will call our recurrent cell. But the standard recurrent network has very simple computation, right? We're going to change that with this rather more hideous structure, right? But the structure is not so hideous. Just to give you an example. Pardon me, how do we decide? Bear with me, right? So here's the complete structure, right? What are the components of the structure? Uppermost thing is remembered cell state. This is the memory that's not affected by any parameters or activations, but you want it to be modified. There are two operations you want. If I'm storing braces, I want to be able to increment braces when I detect a brace. I want to be able to decrement it when I detect a closed brace. So these are two different operations. They're not the same operation, right? So we're going to be doing both. So CT is the linear history carried by the constant error carousel. It carries information through only affected by a gate and addition of history, which is gated. And then you see that there are two controls within in each time, right? There's a multiplicative and an additive control. The reason is we need two operations. One is the decrement, one is the increment, right? If you try to combine the two, it just ends up being a plus. So you end up not distinguishing between the two. So we explicitly introduce two different kinds of operations just to make sure that both of these operations can be performed. And so the first operation is a simple sigmoid unit with outputs in the range 0, 1, which is going to decide how much of what is in memory is going to be passed through. So for example, if I'm currently storing 10 open braces and I find a closed brace, then it must decrement, multiply the output by 0.9, right? So this is, and so this gate over there, that's your forget gate. It tells you how much of what's in memory to forget. And it takes as inputs the current input, the current hidden state, and other stuff. And it helps you forget, right? Now, the second one is trying to increment the memory. So if I'm counting braces, here's a nice way to think about it. First, I need to detect if I've seen an open brace, right? But I also need to know if I need to count, what if it's in a common section? Do I really need to be incrementing my count of braces when I'm analyzing code, right? So there are two components to it. The first, the TANH component, detects the presence or absence of of patterns to increment or decrement. And the second one, which is the sigmoid, the sigma to the left, is the one that decides if this really must be affecting what's in memory. So there are two structures over there. One is the sigma term, which is what is called the input gate, which is a sigmoid operating on some affine function of various terms coming in. And the second is the TANH term, which actually detects patterns. And what really happens is that what is currently in memory over here is going to be, so the ft times ct minus 1 is the outcome after scaling what was previously in memory by the output of the forget gate, right? The second term is it times c tilde t. C tilde t is new patterns that you detect, and it is the gate which decides whether this pattern really must be affecting your what's in memory, right? And then the memory is just retaining stuff, but then you have to use it. So to use it, the output of the memory goes through the nonlinear activation function, which is TANH. And then for some reason, they like to throw in an additional gate, which operates on it to scale it up and down to decide whether it's even useful to pass it on. So some of the computation here looks slightly non-intuitive, but most of it is actually very intuitive, right? And so here is the, and of course, all of these gates depend not only on the input, but also on what's in memory. That's called the peephole connection, but also on two different things. The HT is the non-linearly transformed version of the state, what was in memory, and the peephole connection gives you the raw memory. It's just a question of throwing in lots and lots of gobbledygook into these gates in the hope that they will learn more meaningful functions, right? Pattern detection, says Philip.
What's the difference between H and C again? If they're both what we remember from the previous.
So there is redundancy. We just made it redundant. I won't be talking about GRUs because we're out of time, but please go over the slides. GRUs answer some of these questions. Why have all of this redundancy, right? And so here is the complete circuit. It looks very complicated when I write like so. But then when you look at it piece by little piece, it's not so complicated at all, right? Here is the complete, let's skip this poll, we're out of time. So LSTMs stabilize the memory by eliminating the problematic recurring waits and activations. They update memory based on patterns detected in the input and the current context of what they already remember. In the absence of external cues, they can remember a pattern forever in theory. And they're suited to building pattern analyzers requiring long-term memory, for example, code parsers, right? So here's the complete set of computations within an LSTM cell, which is the operation that happens at one time instant. So the LSTM cell takes in the current input. Then it's going to take in two things from here. It's going to take in the raw memory, but it also takes in a state which has been derived from the memory. These two are kind of redundant, but it does do so, right? And then it produces an output. It also continues to produce a raw memory. This output goes on to subsequent units down the network, and both of these guys go into the next cell, right? So if you look at the computations, the first term over there to the left, is to the forget gate. You compute the first you compute the forget gate, then you compute the input gate, then you can compute the forget and input gate. You also find pattern C tilde. So the forget gate modifies what's in memory. Then the pattern detector C tilde and the input gate also modify what's in memory. Then what's in memory actually influences the nonlinearly transformed state that you compute. It also influences what is in the forget output gate, and then all of these are combined. So again, the processes, I'll leave these to you guys to see what's on the slides, but concept has to be fairly straightforward, and you can always build on it, right? And I actually will go the extra minute. There's a lot of code. Okay, you guys can look at the code, but then here is the problem, right? The problem is back propagation. If I begin looking at derivatives, there are many parameters in this network, right? If I want to compute the derivatives, say for the CT, given everything downstream, look at the various paths through which CT is influenced, right? Does anybody want to be deriving these equations, right? Or same thing with HT, right? And this is incomplete. I promise you it's incomplete. So you don't actually do this. This is where you go back to code. And so leave the class right here. You will not explicitly derive the derivatives with respect to weights. I'll leave this as an exercise if you feel masochistic. But the simpler thing is to go back and say, how do I implement an LSTM cell? And if you implement an LSTM cell, here is the simple math. And the math is very straightforward, right? It's just a series of equations going forward. And we know that when you want to compute derivatives, you can just undo the derivatives going backwards. We've already seen how to do this in the problem of CNNs. And so that's basically all we will do. I have this code over here. This class went on a little too long, but I have this code over here, which you can take a look. This is the forward code, the 6 equations. You can compute the derivatives going backward one at a time. And the entire thing is explained, right? So I leave it to you guys to figure this out. Next week, we will have no classes. The week after, I will not be here. So we're going to have classes on Zoom for at least 1 week after spring break. Tomorrow, I will hold a couple of office hours. And for those of you who have patience at 5 o'clock today, I'll finish the rest of this lecture because there's some components that I left. And so you can come online at 5 p.m. and learn all about the rest of the magic of LSTMs. Yes.